Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back to Nuclear Magnetic Resonance Spectroscopy. We're going to talk about carbon-13 today, and we're going to talk a little bit about structure determination using carbon-13. Carbon has got two main isotopes. One is carbon-12 and one is carbon-13. Carbon-12 has 6 protons, 6 neutrons. Therefore, it's even and it doesn't have different energy states in a magnetic field. If you take carbon-13, it's got 6 protons and 7 neutrons. It's got an odd number of neutrons. So if you have an odd number of protons or neutrons, and you take those elements and you place them in a magnetic field, they will have a quantized spin angular momentum. Therefore, you will have different energy levels. So if you take carbon-12, that's about 98.02%. Carbon-13 out there in nature is 1.08%. This 13 carbon has got an odd number of neutrons. And when you place it in a magnetic field, it will have different energy states. It has got a quantized spin angular momentum, and the spin number here is a half, just like for a proton. So we know that it will have this many energy levels when you place it in a magnetic environment, and that in this case is going to be 2 times a half plus 1, and that is 2. And so you will have 2 states, just like we talked about in a proton. They're very, very similar. So it will have a alpha and a beta state when you place them in a magnetic field. Now the frequency here is different from the frequency that you would have in a proton transition. So whenever you increase the magnetic field, the energy difference would be higher, and therefore the delta E here would be h nu, and there would be some frequency at which there will be a resonance. And each time it relaxes, it will spit out some energy, which will be detected by the NMR machine, and you will get a corresponding peak for it. So every carbon that's in a different environment will have its own separate peak. Okay, so so whenever you have a carbon-13 NMR, you would see a peak for each carbon, and you might wonder, well, why doesn't the hydrogen spectra show up if that also has an I equals half? Well, you change the transmitter, and the frequency here is different for 13 carbon and for the protons. Actually, 13 carbons would resonate at a lower frequency, so you have to change the transmitter. On the NMR machine, you just select carbon-13 and run the spectra just like you would. Now, if you have, let's say, carbon-13 spectra, and you see these lines, each of these would correspond to a carbon in a different environment. And you can see the scale at the bottom is very different from a proton. It goes from 0 to 220. And we're talking about carbons here. Carbon would have different peaks or absorptions in different environments. When you have electron withdrawing groups, the electron density around the carbon is depleted. Then your electron shield will be thinner, the diamagnetic field would be thinner, and therefore you would be resonating at a higher frequency. Whereas if you have a carbon that is shielded, surrounded by electron donating groups or just other carbons and hydrogens, those are shielded carbons, then you would have a lower frequency here. There is a chart that you can look up, and alkyl protons are typically found below 40 or 50. So 0 to 40 is going to be primary, This is in ppm, parts per million, and the scale is very similar to the one that we talked about in hydrogen. We do have TMS at 0 here. Another thing that's very important is you will see at 77, you see this triplet peak. It's actually not really a triplet, it's just 3 parallel lines together, and that is at 77. And 77 is CdCl3, and that is pretty much how you shim that machine. Okay. So here 77 is the peak for CdCl3. So that's one way to know that, you know, this is a carbon-13 NMR, is just look for that if your solvent is CdCl3. And if you have a secondary, that is going to shift a little bit more, 10 to 50, and tertiary would be 15 to 50, about the same region. And if you have quaternary, you would have very weak signals. Quaternary would have a very small peak, and that would be about in the same region, but I would put weak. Okay, that would be for a quaternary carbon. These are for alkyls. Now, if you have electron withdrawing groups such as chlorines or bromines or nitrogens, it could shift from between 10 to 65. If you had an oxygen, it could shift 50 to 90. And just like in a proton spectra, if you had double bonds, then your region really shifts over here about 100 to 170. Benzenes and, you know, double bonds would be in that middle region here. Over here, you would find your carbonyls. So alkyl groups, alkenes, carbonyls. That's pretty much the region. Your triple bonds are actually 60 to 90. So the triple bonds would be in between the alkyl, sp3, and the alkene, sp2, would be your triple bonds. All right. So those are some regions to remember. Now, if you have a NMR, for carbon-13 NMR, and you want to run it, you have to do multiple scans. Sometimes you do it overnight, 240 or more, and to get these signals to show up, you know, above the noise level. Proton NMRs don't need that many scans, 16, 32, 64, and so on, depending on how concentrated the sample is. Obviously, if you have very concentrated samples, then you have a lot more resonance, and you would have a stronger or intense peak. So over here would be your intensity, and over here would be the shift, chemical shift from TMS due to electron withdrawing groups or other functional groups. Okay, so that's just a little blip about carbon-13. It's a huge field. All right, let's look at these 3 spectra. All of them have the same formula, but different 13 carbon graphs, which would make them isomers for 5 carbon. We're going to figure out what those are just by using a 13 carbon NMR without, you know, using a proton or an infrared or even a mass. Let's look at first the formula. The formula here says C5H11Br for all 3. So isomers of that. The first thing you should do is just do a really quick IHD, index of hydrogen deficiency. So this is going to be 2n plus 2. N is the number of carbons minus m, the whole thing divided by 2. So here you're going to have 10 plus 2, 12, minus m is 11, but in the case of bromines or halogens, you add 1. So that is going to be 12 divided by 2. That is 0. So these are saturated compounds. That means there's no double bonds or rings. Next, what are the possible isomers for this 5 carbon structure when it's saturated with a bromine? Another very important thing about carbon-13 spectra is the spin-spin coupling between carbon and hydrogen. So in carbon-13 spectra, carbon and hydrogen have I is equal to half, and they do obey N+1 rule. Carbon here, we can see splitting of carbon by hydrogen at certain frequencies, and we have a technique for doing that. There are actually two very important techniques, actually more than that, but let's just talk about two. One is off-resonance decoupling, and the other one is DEPT, depth, distortionless enhancement by polarization transfer, whatever that means. These two, basically, in a nutshell, would provide information about the number of hydrogens on a given carbon. So this is why you will see sometimes on spectra, carbon-13 spectra, you would see that these lines would have a label. In this case, it's saying CH2, 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 CH3. So using these techniques, they have figured out for each of these carbons how many hydrogens are there on them. Let's take, for example, this molecule. Let's say I have a molecule like this. We have a carbon chain, and one of them is just a primary with 3 hydrogens. The other one is a secondary with 2 hydrogens. The other one is a tertiary with 1 hydrogen, and this has a quaternary, let's say, with no hydrogens, or it has got other 3 groups on it. So let's say we have a bromine or a chlorine here, and 3 chlorines here. Could be anything that doesn't have hydrogens. That's, I'm just putting halogens for that. So in each one of these cases, you can see the number of hydrogens on each of these carbons using these techniques. And because they both have I is equal to half, they would obey the N+1 rule. So let's label these carbons, let's say A, B, C, and D. Carbon D has got 3 hydrogens on it. So if you were to apply the N+1 rule for this, if I take CD and use the N+1 rule, N is the number of hydrogens, N is going to be 3. Therefore, N+1 for this carbon, the splitting by that, would be 4. So you would have a quaternary peak. If you take CC, carbon C, the number of hydrogens, so in this case, I'm going to write this N is the number of hydrogens on carbon. Neighboring hydrogens do not split the signal. Neighboring hydrogens will not split the carbon signal. What that means is this carbon is only looking at these 3 hydrogens. It is not split by these hydrogens. The same is true for this carbon. It's only split by the hydrogens that are directly connected by it through 1 sigma bond, and it's not split by these neighboring hydrogens. So therefore, that is very different from the way proton NMR spin splitting or coupling works. This is only be from the hydrogens directly connected to that carbon. In this case, N is equal to 2. There's just 2 hydrogens there. Therefore, N+1 would be 3. And you have 2 hydrogens on a carbon or a CH2, that would be a triplet. If you take this, again, there's only 1 hydrogen on there. N is equal to 1. Therefore, N+1 would be 2. And that would show up as a doublet. The last one here has no, Ca has no hydrogens on it. N is 0. Therefore, N+1 is just 1. And therefore, it's going to be a singlet. So this is a very easy way that of figuring out how to find the number of hydrogens on each of those carbons. That's very valuable information. If you have that information, you may not even need a proton anymore for this. So let's draw a kind of a theoretical or schematic spectra for this. So let's say 0 is where you have TMS, and 77 is where you have CdCl3. And let's look at what's in between here. Typically, this would be in between in the alkyl region. This CD would give you a quaternary peak. And the more hydrogens you have, the intensity of that carbon also typically increases. And so you'll have a quaternary peak for that D carbon. You would have a triplet for this CC carbon, and you would have these are going to be very D-shielded, these carbons, because this one especially is next to 3 chlorines, okay? So it's kind of like somewhere near this. This is going to be next to a bromine and next to an electron withdrawing CCl3 group here. Therefore, this is going to be the next most D-shielded. This is next, and this is going to be shielded compared to all of them because it's away from all of these groups. It's 1, 2, 3 sigma bonds away from bromine, and 1, 2, 3, 4 sigma bonds away from chlorine. So by the time that inductive effect gets to it, it hardly even feels it. So that's probably close to about 10 ppm on the delta scale, about 10. And this Ca would be close to about 77. So the next one here would be a doublet. And then this one would be your Ca. And this is just not drawn to scale or anything like that. So there you go. So that's kind of what you would expect when you apply these techniques to a molecule like this. Once you have this information, it's a lot easier then to put together a structure of an isomer given the formula. In this case, this is going to be C4, 6 hydrogens, a bromine, and 3 chlorines, Cl3Br. Now, another important thing that you would notice on all of this is the CdCl3 peak at 77. Now, this is a coupling between the carbon and the deuterium. Now, I'm going to just put a note here. Deuterium has an I value that is 1. Therefore, 2I plus 1 is going to be 3. So therefore, you can see 3 levels here, which is why you see those 3 lines. And it's a lot more complicated than that, but that is why you see CdCl3 giving you a line like that. I mean, it's kind of important because most of your spectra are run in CdCl3, and you would be seeing that. And that is going to be at 77 ppm. So I'm just putting that as a note. All right, let's look at these 3 spectra here. Let's call this A, B, and C, and try to figure out if we can come up with a structure for these based just off of the 13 carbon NMR. Let's work out A here. So I'm going to do it right here. This is A. A has got 4 CH2 groups and 1 CH3 group. And I'm sure by now you'd kind of have figured out what that is. So basically all 5 carbons here have different peaks. That means they are in different environments. There's absolutely no symmetry that makes any of these carbons identical. So where would you put your bromine? Would you put it here, 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 or here? If you put the bromine, let's say here, then you would have these 2 being the same as this. If you put the bromine here, there is a possibility that all these would have different peaks. However, you wouldn't have 4 CH2 groups. So the only really place to put it would be here, or here would be identical. And the rest would be giving you, well, 4 CH2 groups and that is what we have, and one CH3 group. And that's what you see here. Say, if you label this A, B, C, D, E, you could say that these would correspond to A, B, C, D, E carbons. Okay, again, you have to kind of switch your frame of mind here. We are looking at carbons. We're not looking at hydrogens. We've been looking at hydrogens all this time. So now you got to kind of switch gears and look at carbons. Let's look at the next one, B. Let's look at the B spectra here and see what you have. You have CH2, CH2, CH, and CH3. So this is B, has two CH2 groups, one CH group, and one or two. Well, we don't do really integration here, but the CH3 group here is almost twice the height of these CHs. So there's only one CH3 peak, but it probably has got two methyl groups, very tall. So it would have more than one CH3 in it. Probably about two when you estimate. Okay, I would say two CH3 groups. So what would be a possible structure for this? Two CH2 groups, a CH and a CH3. Well, let's try putting it together. Two CH3s. How would you have two CH3s that are identical? They've got to be on the same carbon. So here's a carbon, and it's got two carbons on it, so these are identical. So these are probably this two methyl group. So you have an isopropyl structure. Let's look at the others. You have a CH. Well, if you have an isopropyl, you would probably have a CH here. But, well, how do you know whether you don't have a bromine here? Let's look at the others. And you have two CH2 groups. So you have two CH2 groups. So you have 5 carbons total. And if you put the hydrogens in, these are going to be your CH3 groups. And you can see they are identical in every way. So these two are your two CH3 groups. This is going to be a CH. If you put a CH here, you don't have two bromines. You only have one bromine. Therefore, you got to have a CH here. You have two CH2 groups. So let's put that here. So you can see from this graph, the CH2 groups are more de-shielded, therefore they must be next to the bromine. So if you take this and label these A, B, C, and both these are identical, so they're D. You can see there is a plane of symmetry here, and this, when you rotate, they are going to be identical. There is no way the machine is going to be able to distinguish between them, because this is really not even a chiral center here, and so you're not going to be able to see that. So over here, A would be the most de-shielded, and that would be A. The next one would be B. C is your one that's shielded next, and then D you would see is twice as tall as the other peaks because you have two of them. And this is the most plausible structure. You really cannot move this bromine anywhere else because that would create another methyl group, which you don't have. All right, so this is a very straightforward way of figuring out structures just from your 13 carbon NMR. Let's look at C here. Let's write down the data. There's one carbon here that's very de-shielded. So 1C, that's a quaternary carbon. Quaternary carbon. There's no hydrogens on it. There's another carbon here around 40, one CH2 group. And one CH3 that is very tall. And since it's very tall, we would suspect that there are more of these groups buried underneath that peak. And it's about twice as tall as the other one. So let's say for now there may be two CH3 groups buried underneath that peak. Then you have another CH3. So one CH3 peak, and that's very shielded. So where do we even start? Let's start with the ppm values. This is a quaternary and it's very de-shielded, which means it's going to have the bromine sitting on it. Otherwise, why would it be that de-shielded, right? So you have a quaternary carbon. That means you don't have any hydrogens on it, and the bromine is on here. And because it's quaternary, you're probably going to have 3 carbons on it. So that's 4 carbons. Where is carbon number 5? Obviously, you have a CH2 group. One of these would be attached to a CH2. Let's look at that. So here, if you're going to do another CH3 group that's shielded, it's probably going to be attached to this, this, or this. And it really doesn't matter which one, because these are all going to be rotating and you get the same structure, rotamers. So over here, let's look at this. Let's put the hydrogens for this and see if this is a plausible structure. You have a CH3 here and a CH3 here. You have a CH2 here and a CH3 here. This carbon is the most de-shielded. Let's label this A. And these two are, you can see as a plane of symmetry here. Therefore, these are identical. So when you have symmetry, the number of peaks would collapse. So here you call this the same as this, B. And this is different. There's no other CH2s. And this is D is also unique. Now, A would be the most de-shielded because it's directly connected to that bromine. Next would be these 3. And you can see CH2 is next. That's going to be C. And you can see the B's are 2 of them. Therefore, that's why you have a very tall peak here. The intensity is high because there's more absorbance by these 2 B carbons. Now, D carbon is the methyl group. And you can see why that's the most shielded, because it's 2 carbons away from this bromine, whereas these methyls are only 1 carbon away. Therefore, these methyl groups are more de-shielded than this methyl group. So this is a good way to find out the layout of a molecule just by using 13 carbon NMR. What would you expect for an isomer like this? How many peaks? Let's say we had another spectra, and I don't have space for that. Let's say we had a molecule like this. Let's say we had a spectra like this. What would you expect? How many peaks would you expect for this isomer? The same formula as that. So this is just, part of the group. Let's see how many different types of carbons are there. You can see these 3 carbons are interchangeable by rotation, and they are identical in every way. They are all 1, 2 carbons away from that bromine. All of them. So there are 1, 2, 3 sigma bonds between this carbon and this bromine for all 3. Therefore, the chemical shift would be identical. And they would be the most shielded of them because they're furthest away from bromine. So bromine is going to pull on this carbon, and that's going to pull very slightly on this carbon. And that would, there's hardly a tug on these sigma bonds. So as the distance increases, then the inductive effect falls off dramatically. So these 3 are going to be in the same delta. This would be in a separate delta because there are 2 sigma bonds from bromine, separating that carbon. And this carbon would be right next to it, and that would be the most de-shielded. So let's label them A, B, and all these 3 carbons would be C. So you would have the tallest peak between, let's say, 0 and 10 around for C. And that would be almost 3 times the height as this or this, because these are just individual carbons. And the next one would be B. And the next one would be A. And A would be the most shielded. And let's say this is going to be A. And quaternary carbons, as we said before, always very low intensity absorptions. And this would be C. And that would be another isomer. So we can figure out isomers just given a 13 carbon spectra. We don't even need a proton at this point. We will come back with more examples, guys, for you, and talk a little bit more about carbon-13. Welcome to carbon-13 NMR spectra. If you have any questions, please let me know. Talk to you soon. Bye.